So let's take a closer look at divergence in 3 dimensions. So to get us started, I want you to begin by making a love note to yourself that 2-dimensional divergence naturally extends into 3 dimensions. All we do is simply add that third component. So let's take a closer look. Divergence in space. So if vector F is a differentiable vector field defined on some region in R3, then the divergence is defined as follows. So you have the partial derivative of F with respect to X plus that partial derivative of G with respect to Y. And keep in mind, we note that this is that 2-dimensional divergence. And since now we know our vector field here is in 3 dimensions, we add that third component. So this is plus the partial derivative of H with respect to Z. And we can alternatively rewrite this in our differential form, df dx plus dg dy plus dh dz. So this is our 3-dimensional divergence. And our interpretation of 3-dimensional divergence remains the same. The divergence of the vector field still measures the expansion or contraction of a vector field at each point. So the divergence, again, measures the expansion or contraction of the vector field at each point. So we're thinking to ourselves, how much of that vector field is passing into a surface? Or how much of that vector field is passing out of a surface? So let's go ahead now and think about the interpretation and the derivation of the divergence in space in a little bit more detail. To attain the divergence of a vector field in 3 dimensions, we're going to need to take the dot product of the del operator and the given vector field. So just a friendly reminder, our del operator, you want to keep in mind that this is not a vector, but it's the operation that's applied to a function to get the partial derivatives. We use this same vector operation when we looked at the gradient. So to attain that divergence, we're taking the dot product of del and the vector field. So del has components d dx, d dy, and d dz for space, and we're dotting this with that 3-dimensional vector field defined as f, g, h. And in applying the dot product, we end up with the partial derivative of f with respect to x plus the partial derivative of g with respect to y plus the partial derivative of h with respect to z. And if we convert this to the equivalent subscript form, we have the partial derivative of f with respect to x plus the partial derivative of g with respect to y plus the partial derivative of h with respect to z. And now we should also make a little note to ourselves that since we applied the dot product here, the divergence is a scalar. So the dot of del with the vector field is a scalar, or a real number. It's a constant value. So now that we see where this comes from, we're ready to state the definition. And we say that the divergence of a vector field defined by the components f, g, h that is differentiable on some region D in R3 is defined as div of the vector field f. And as we just saw above, this is the dot product of del with the vector field. And this is what produces that scalar valued result, the partial derivative of f with respect to x, the partial derivative of g with respect to y, plus the partial derivative of h with respect to z. Now, one more note before we look at examples here is that what happens if del dot the vector field is equal to 0? Then thinking back to our 2-dimensional divergence, we know that this implies that the vector field is source-free. So if the dot product of del and the vector field is 0, then the vector field is source free.